Hello, I would like to do a problem here for you. This is in section 3.1. It's actually quite amazing material, but you might find it to be a bit tedious to go through this. So let me get the right file here. I sort of copied it in two different ways. Let's see if we can get this. All right, here we go. So here's the question. I'm going to do number 8. And the idea here is to, let me see if I can find it. Okay, so here we go. So this is, we're going to try to solve this differential equation using power series. And it's a very interesting technique. The idea is that you allow yourself to have a solution or the form of a solution. And I'll go through this with you. And, okay, so here we go. So here's our differential equation right here. So the idea is you write down these power series. Here's y. You just assume that y is this infinite sum. And if you differentiate this term by term, you get an expression for y prime. Now, right here, substituting the y into the differential y prime into the left-hand side of the differential equation, you see that you get this expression here. And so I'm now simplifying that, and I finally arrive at this form right here where I have things lined up very nicely. Actually, the very next line, these are lined up very nicely. Now the idea is that, okay, this is the left-hand side of the differential equation, and then on the right-hand side of the differential equation, if we check back up here, we just want y. Okay, so we have the summation. N equals 0 to infinity of this c sub n x to the n. Now what we're trying to do is to find a relationship, a recursive relationship between the coefficients of y, and try to see if we can determine what function are the solutions. So the first thing we see by comparing this term, see if you take 2 times c1, that has to be equal to the first term, or that'd be c0, and that's where this first equation comes from. So that tells us that c1 is equal to c0 divided by 2. So c0 will be our initial value, shall we say, or that's our degree of freedom. Okay, now if you look at the next part, you see right here, if you plug in n is equal to, so right here, if you plug in n is equal to 1 into this series, you get 2 times c2, let me write this, times 1 plus 1 is 2, plus 2 times c1 times 1 is c1. Then you can solve this for c2, and we arrive at the following, that c2 is in fact equal to minus c0 divided by 8. Now what you're trying to do here is to see if you can find a nice formula for the coefficients. And this, you should expect to spend some time on this. It doesn't happen immediately. So let's see what else is going on here. Okay, oh, moving on. So then I'm experimenting a little bit here with C3, and I arrive at this formula here. C3 is actually, it's C0 divided by 16. Okay, I do the same thing for C4. So starting here, 2 times C4 times 4, or I'm sorry, start up here, 2 times C4 times 4 plus 2 times C3 times 3 is equal to C3. Solving this equation here and here for C4, we see we get minus 5 over 128 times C0. And so you can see the form of the equation is coming out here, right? Now, part of the exercise was to look back and try to imagine which one of our functions that we know are known power series this might be. And if you look at the number 12, it sort of seems like we might be in business. So what we're thinking is that perhaps at this point, it sort of looks like it, but if I write this down, I write 1 plus x to the alpha, right? that's equal to 1 plus alpha x plus alpha times, well, you can look at it yourself. It just keeps going on like this. All divided by 2 factorial times x squared, right, plus dot dot dot. So you begin to look at that and you think to yourself, could this be the case when alpha is equal to 1/2? It checks out in this term. Now let's see, if you plug a 1/2 in here, it checks out here. So it seems to be following the pattern. Now what I'm going to do is actually prove this, and this should illustrate at least an application of proof by induction that you've seen in algebra course, and sort of show you where this might be applied. So let me open up this next document and we'll look at that. Okay, so here we go. I'm going to try to prove that in fact this is the correct answer. So the claim is that as in equation 12 on page 195, I'm hoping that my coefficient c sub n is actually equal to c0 times this mess. So the way we prove things like this, you may remember from algebra, is proof by induction. And what we're going to do is we're going to assume it's true for the first, or not assume it's true, we're going to prove that it's true when n equals 2, and then we're going to use our induction to prove it for all n. So we know that if n is equal to 2, we know from our calculations that we did on the previous slide that C2 is actually equal to C0 times 1/2 times 1 minus 1 over 2 factorial. Well, that's correct. You can just look at it. So you have, up in the numerator here, we have a minus 1/4. In the denominator, we have a 2. So that simplifies to be minus 1/8. So our hypothesis here, it's true when n is equal to 2. So now we will assume the claim is true for the value n minus 1. That is, we are going to assume, whoa, hold on here. Something's going crazy. So we're going to assume we assume, sorry about that, that in fact, oh shit, oot. Something's going a little crazy here on my screen, sorry about that. So, oh, I know what it is. Okay, I'm leaning, don't ever lean on your trackpad and try to write at the same time. Okay, so we're going to assume that this is true. In other words, C sub n is in fact equal to that. Okay, so here's how we're going to proceed with the proof. We know that 2 times C sub n times n plus 2 times C sub n minus 1 times n minus 1 is C sub n minus 1. So we solve this equation for C sub n, and we notice that, just using some algebra, that C sub n is in fact equal to 3 minus 2n times C sub n minus 1 divided by 2n. So then what we do is we essentially use our induction hypothesis. We plug in, so here's C sub n, right? So we plug that into the formula right here. This is also C sub n by our assumption here, our hypothesis. And then we get this expression. Okay. Now, we do a little calculation. If you look at this last bit here, this 3 minus 2n, 3 minus 2n is actually equal to this. And you may wonder, why do I want to write it in this funny way? Well, I know by looking at my expression here that there's this 2 that's in the denominator that I'm not really interested in seeing there. I'd rather just see n factorial. So I know that this term here had better have a 2 that I can factor out. And otherwise we're in trouble. So in fact it does work out fine, because then C sub n is in fact equal to, and here we go, all this mess, and here I'm substituting in my new value for that, right? And then lo and behold, the 2's cancel and we have our nice formula. So this proves that all the coefficients are right, and so in fact the solution to our differential equation is given right here. This is the square root of 1 minus x times C0. Now, the solution we must find out on what interval this power series represents a solution. So this requires us to find the radius of convergence. So we look at the absolute value of the ratio of coefficients. So we look at the absolute value of c sub n divided by c sub n plus 1, and we can calculate that and simplify the algebra. It gives us this, and we see that if we take the limit as n goes to infinity, the limit is 1. So by our convergence tests, we know that y converges on, in fact, the real interval minus 1 to 1. So our radius of convergence is 1. So I hope this helps. These problems can be quite involved, and I think what you'll find is that you'll really get good at being accurate with your notation, because some of the trickier elements of this. Let me show you some of the. I kind of went through these quickly, but let me go back for 1 second to show you where some of the things can happen here, though, some of the problems. Let me see if I can get in there. Oh, God. Okay, I'm looking for the file that I just had opened here. Okay, there it is. Okay, so let me show you where some of the details that may drive you crazy are. So look in here. Look at this. Okay, right here. I run over this fairly quickly. Look right here. So you see, when you multiply this, 2 times x plus 1 times this thing, notice how we get the. Notice how here we have a coefficient. Gosh darn it. Notice here, the exponent of x is n minus 1. So combined with this x here, when you use the distributive law, that's what creates this being an exponent of n, because we have to use the exponent laws, right? And so you get this 2 times c sub n to x times n times x to the n. And now similarly over here, you see we just have this 2 times cn n, but we still have this exponent of n minus 1. So, okay, then what we have to do is try to write an expression so that we can group together and find the coefficient of n. So you notice the first thing I do is realize that this 2 times c1 comes from this part. When you plug n equal to 1, that's where you get this. So I take that term of this series and move it out to the front here, and then what you're looking at is the following. Notice now I start with n is equal to 1, and rather than writing having the exponent of n minus 1, I have an exponent of n, but then I must change the subscripts of must increase the subscripts and the n by 1. See, if I increase n minus 1 by 1, I also have to increase n by 1. So that you have to be very careful that this is precise and exact. So that might be where some of the troubles come in when you're doing these problems. Okay, have fun. I'll do some more examples. I'll talk to you later. Thank you. Bye.